Hey there guys, welcome to my walkthrough of the Edexcel A Level Maths Sample Assessment Material Paper 3, which is Statistics and Mechanics. So traditionally, this is the one people find the hardest. I understand why. The paper is linked down below, along with, if we need it, the large dataset and the formula sheet, as well as my playlist with all three sample paper walkthroughs. Let's do this then. Okay, number one. So the number of hours of sunshine each day for the month of July at Heathrow are summarised in the table below. A histogram was drawn to represent these data. The 8 to 11 group was represented by a bar of width 1.5 centimeters and a height 8 centimeters. Part A wants us to find the width and height of the 0 to 5 group. Okay, so in the histogram, the area of the bar represents the frequency. So, looking at the 8 to 11 group, there was a frequency of 8. So, from that then, we know that 1.5 times 8 so 1.5 centimeters times 8 centimeters which is 12 centimeters squared. So 12 centimeters squared represents 8. Or represents a frequency of 8. So if we divide by 8, then that gives us 1.5 centimeter squared. Represents a frequency of 1. Now, in the 0 to 5 interval, there is a frequency of 12. So we can find the area of the bar. So the area for that then is going to be 18 centimeters squared, because it's 1.5 times 12. Okay, so that needs to be the area of the bar. What we also now need to do is work out a scale for the width. So, the 8 to 11 group has an interval width of 3 that was represented by 1.5 centimeters. Every 1 then is 0.5 centimeters, so the width of 0 to 5 is 5 times 0.5 which is 2.5 centimeters. And then the height is the area divided by that. So 18 centimeters squared divided by 2.5 centimeters. And that gives us 7.2 centimeters. Okay, then part B wants us to find estimates for the mean and standard deviation of these data. So our calculators can do this very easily for us. What we are going to need though, because it's grouped frequency, we are going to need the midpoints. So 0 and 5 is 2.5. 5 to 8 is 6.5. 8 to 11 is 9.5. 11 to 12 is 11.5. And 12 to 14 is 13. Okay, so what we can now do is put this frequency table into our calculators. For this, you do need frequencies turned on. So, go into the menu, then stats, then on variable, then press the on button to get back to the main screen. You then want to press shift and setup, go down to statistics, turn frequencies on, go back to the menu, stats, one variable. Now you should be in a frequency table. For the X values, put in the midpoints. For the frequencies, put in frequencies. When you put all of those in, go back to the main screen, and then you want option, and then variable calculations, and you should get this screen. So, for us, our variable is y, not x. So, y bar is equal to, now it's set to 3 sig figs, so that would be 6.63. And our standard deviation sigma is this guy here, sigma x, which would be 3.69. Okay, then next up, the mean and standard deviation for the number of hours of daily sunshine for the same month in Herne are 5.98 hours and 4.12 hours, respectively. Thomas believes that the further south you are, the more consistent should be the number of hours of daily sunshine. Part C, state giving a reason whether or not the calculation in part B, the calculations in part B support Thomas's belief. So, You do also need to know for this that Perrin is south of Heathrow. You have a different large data set each year, and theoretically you learn or you're going to need to know about that data set. So don't go worrying here that you don't have a map to go with it. So Perrin is south of Heathrow. If we compare the results, so the mean in Perrin was 5.98. The mean in Heathrow was 6.63. The standard deviation in Perrin, however, was 4.12. In Heathrow, it was 3.69. So a smaller standard deviation means more consistent data. So the data is actually more consistent in Heathrow. So given that Perrin is south, Thomas's claim is not supported by the data. Okay, part D wants us to estimate the number of days in July at Heathrow where the number of hours of sunshine is more than one standard deviation above the mean. Okay, so the first thing we're going to need to work out then is the mean at 1SD. So 6.63 at 3.69 if we carry on going to 3 sig figs, that's 10.3. So, we want the number of days where there were more than 10.3 hours. So, we definitely want the top two intervals. So we're having 5 to start. And then we're also going to need a part of the 8 to 11 interval. So we need to work out what proportion we want of those 8. So 11 take 10.3 is 0.7. The whole interval is 3 wide. So we want 0.7 out of 3 of 8. So that's 0.7 over 3 times 8. Now that is going to give us 6.86. So we would round that up to 7. Okay, next up, Alan models the number of hours of sunshine each day for the month of July at Heathrow as normally distributed with mu 6.6 and the variance as 3.7 squared. T wants us to use Alan's model to predict the number of days in July at Heathrow where the number of hours of sunshine is greater than one standard deviation above the mean. Okay, so what we need to do is find the probability that the probability is greater than 10.3, and then multiply that by the number of days in July, which is 31. So, we want the probability y is greater than 10.3. Now our calculators can do this, so you want distribution normal CD. For your lower bound, put in 10.3. For your upper, you can put in, I put in 24 hours in a day. You can put in anything as long as it would be greater than 24. For sigma, put in 3.7 and mu 6.6. And that will give us 3 sig figs 0.159. So then the number of days as an estimate is 0.159 times 31, and that is going to give us 4.92, which we could probably get away with rounding up to 5. Okay, then part F, the final part, we want to use our answers to D and E to comment on the suitability of Alan's model. So, we worked it out as 7 days. Alan's model has worked it out as 5 days. Now, in terms of the scale of things, 5 is quite far below 7. So we should say something like that and follow it with, therefore, Alan's model may not be appropriate for this data. Alright, moving swiftly on. Number 2, that's just as fun. So, a meteorologist believes that there is a relationship between the daily mean wind speed, W kilometers, and the daily mean temperature, T degrees Celsius. A random sample of 9 consecutive days is taken from past records from a town in the UK in July, and the relevant data is given in the table below. The meteorologist calculated the product moment correlation coefficient for the 9 days and obtained R is 0.609. Okay, part A wants us to explain why a linear regression model based on these data is unreliable on a day when the temperature is 24 degrees Celsius. Okay, so let's have a look through the table. Does the data go that high? No, it doesn't. So the highest temperature recorded in the table, I believe, is 19.3. So, we only have reliable data up to that temperature. So, if we were to use it for a temperature of 24 degrees Celsius, we are assuming that the relationship would remain linear. So, assumption is the mother of all fuck-ups, so we can't just assume that the model would work for any values. So really there then you'd want to say if 24 is far above any data given in the table, so the model would be unreliable. But B wants us to state what is measured by the product moment correlation coefficient. So that measures the link between the two variables. So here it's the strength of the link between W and T. Okay, then for part C, stating your hypotheses clearly, test at the 5% significance level whether or not the product moment correlation coefficient for the population is greater than 0. Okay, so for this then, for our hypotheses, we need to think about our p-values. So our null hypothesis, that's always the one where your thing is set equal to a value. So here for us, h0 is that p is equal to 0. Now h1, well, we want to test whether it's greater than 0. So h1 is that p is greater than 0. So it's a one-tailed test. All we need to do is find the critical value, which we can do using the tables. So the critical value, so these are in your formula sheets. So our sample size is 9, we're at the 5% level, so we want this highlighted value 0.5822. Now, our value for R was 0.609, which is greater than 0.5822. So, because that is greater than, we reject h0 because there is evidence that the product moment correlation coefficient is greater than 0. So there is evidence at the 5% level that the let's just call it PMCC is greater than 0. Okay, then using the same 9 days allocation from the large data set gave t bar 27.2 and W bar is 3.5. So the question said, use your knowledge of the large data set. Suggest giving a reason, the location that gave rise to these statistics. So, by the time you're watching this won't be the large data set that you're using. So, I've just put the answer here from the mark scheme. So, because there was a higher mean temperature, that definitely suggests that we're not in the UK. That makes sense. And then because there was a lower wind speed, that suggested not near the sea. I live right by the sea, can confirm we get quite strong winds, so that makes sense too. So the people that used this large data set would hopefully have been well versed in the countries that are in it and whereabouts they are, so that would have led them to Beijing. As I say though, this won't be your large data set, so don't dwell on it too much. Okay, number 3. So a machine that cuts strips of metal to length L centimeters, where L is normally distributed with a standard deviation of 0.5 centimeters. Strips with a length either less than 49 or greater than 50.75 centimeters cannot be used. Given that 2.5% of the cut lengths exceed 50.98 centimeters, we want to find the probability that a randomly chosen strip of metal can be used. Okay, so before we worry about the probability that a strip can be used, we are gonna need to know the mean of the distribution of L. So, we know then that L is normally distributed, and we don't know the mean, so it's mu, and the variance is 0.5 squared. Now, what we do know is that 2.5% of all strips are greater than 50.98. So, 50.98 is there. We know that this area is 0.025. Then we know that mu is in the middle of this. And we know the area in all of this left part is 0.975. Now, hopefully you know that Z values are equal to x bar minus mu over sigma. Now, we know x bar is 50.98. We know sigma is 0.5. What we need to find is z. So we can do this on our calculators. There is an inverse normal function. So going to distribution on mine then is number 3. So we can get on the z is the inverse normal of 0.975. Now when you're in the inverse normal, you put in the area as 0.975. Mu is equal to 0 and sigma is equal to 1. Now that will give us 1.96. So now we know then that 1.96 is equal to x bar, which is 50.98 minus mu over sigma, which is 0.5. Now if we multiply through by 0.5, we get 0.98 is equal to 50.98 minus mu and that then leads to mu is equal to 50. So, what we can now write down then is the full distribution. So, L is normally distributed with a mean of 50 and a variance of 0.5 squared. So, now that we know the distribution, we can find the probability nice and easily using our calculators. So we now want the probability that L is greater than 49 but less than 50.75. So, in your calculator we now want normal CD, lower is 49, upper as 50.75, mu as 50, sigma as 0.5. Stick those in, press equals, and you should get 0.9104. Cool. Okay, then for part B, 10 strips are selected at random. Work out the probability that fewer than 4 cannot be used. Okay, so this is now a binomial situation. A strip either can or cannot be used. So, the first thing we can do is work out the probability a strip cannot be used. So, that's 1 minus the probability a strip can be used, which we just found. So that's 1 minus 0.9104, which is 0.0896. Now, we need to define a variable. We can't use L because that was the length of a strip. So I'm going to say F for 40, so let F be the number of strips that can't be used. And then F has a binomial distribution of 10, 0.0896. From this point, our calculators can now do this for us. The probability F is less than 4. Is the probability F is less than or equal to 3. So on your calculators, go into binomial CD, put the numbers in, and we should get 0.991. Okay, then for the final part, a second machine cuts strips of metal of length x centimeters, where x is normally distributed with a standard deviation of 0.6 centimeters. A random sample of 15 strips cut by this second machine was found to have a mean of 50.4 centimeters. Stating your hypotheses clearly and using a 1% level of significance, test whether or not the mean length of all strips cut by the second machine is greater than 50.1 centimeters. Okay, so starting then with our hypotheses, H0, the null, is always the one where whatever you're dealing with is equal to a value. So H0 is going to be the mu is equal to 50.1. H0 is going to be, H1 is going to be that mu is greater than 50.1. Now, under H0, x bar is normally distributed with mu of 50.1 Now the variance when we're doing the samples, remember, is standard deviation squared over n. So here 0.6 squared over 15. So it's worth noting that our standard deviation S is 0.6 over root 15. Now, the value that we want to test is the mean that we found from the sample. So we want to know how likely is it that the mean of a sample will be greater than 50.4. So we want to calculate the probability that x bar is greater than 50.4. Okay, so for this you need normal CD. For your lower bound, use 50.4. Your upper bound, just use something massive. I used 1000. For sigma, remember that's 0.6 divided by root 15, and mu was 50.1. So you should get 0.0264. Which is 2.64%. Now, 2.64% is greater than 1%. So that means we accept H0 and reject H1. And then you need to finish with a statement. So think about what we were finding. We were trying to find evidence whether or not there was evidence that the mean length was greater than 50.1. So we should say there is not significant evidence at the 1% level that the mean length is greater than 50.1. Because that is the value of mu that we were testing. Cool. Okay, number 4. Given that probability of A is 0.35, probability of B is 0.45, and the probability of the intersection is 0.13. Find part A, the probability of not A given not B. Okay, so I'm going to whack these in a Venn diagram. So, if we call this circle A, this one B. Now we know their intersection is 0.13. Now the probability of A altogether is 0.35, so the probability of just A without B is 0.35 minus 0.13, which is 0.22. And the probability of just B is going to be 0.45 minus 0.13, which is 0.32. Now, the probability then on the outside of the circles is going to be 1 minus these three added together. So 0.35 add 0.32 is 0.67. So the outside is 0.33. Now, we want probability of not A given not B. Now, whatever you are given, so here, given not B, that probability goes on the bottom of the fraction. So we're going to have something over 1. The probability of B is 0.45, so the probability of not B is 0.55. Now we also want, we want the probability of not A given not B. So we now need to work out the probability of not A given that it's not B. So that's just part on the outside of the circles. So that's 0.33. So then that is 3/5. Or 0.6. And part B wants us to explain why A and B are not independent. So, we're even given this. If they are independent, then the intersection is equal to the probability of A times the probability of B. So, all that we need to do here is find the probability of A times the probability of B. So that's 0.35 times 0.45, which is 0.1575. Which is not equal to 0.13. So then you would just say, therefore, the events are not independent. Okay, next up, the event C has the probability of C equals 0.2. The events A and C are mutually exclusive. That means their intersection is 0. They can't overlap. and the events B and C are statistically independent. We want to draw a Venn diagram to illustrate the events A, B and C, giving the probabilities for each region. Okay, so nothing has changed in the A circle because there's no overlap between A and C. So, straight away, we can put 0.13 in there between A and B, which puts 0.22 again in circle A. Now, because B and C are independent, we know the probability of B times the probability of C is equal to their intersection. So that means the probability of their intersection is 0.45 times 0.2. Now that is 0.09. So that's in here. Now we know the probability of C is 0.2. So that means we have 0.11 in there. Now, for just B, we know the probability of B altogether is 0.45, so we need to subtract 0.09 and 0.13. So that is going to give us 0.23. And then we need to work out what is in the rectangle. So, if we add all of these together, we have 0.35, 0.58, 0.67, 0.78. So 1 minus 0.78 is 0.22. So that is the Venn diagram. Okay, then the final part wants us to find the probability of B union C all dashed. So, that means one minus the probability of B union C. So, that is B union C is 0.45, add 0.11 to 0.56. So this is 1 minus 0.56, which is 0.44. Okay, number 5, the final stats question, thankfully, because mechanics is a lot funner. So a company sells seeds and claims that 55% of its pea seeds germinate. Part A wants us to write down a reason why the company should not justify their claim by testing all the seeds that they produce. Okay, so pea seeds are obviously tiny. They're going to produce millions of seeds. How can they test them all? They can't. So we could say there'd be far too many to test. If they did test them all, then either the seeds become plants or they don't germinate. So they would have no seeds to sell if they tested them all. Something like that, and you are golden. Okay, then for part B, a random selection of the pea seeds is planted in 10 trays with 24 seeds in each tray. Assuming that the company's claim is correct, calculate the probability that in at least half the trays, 15 or more of the seeds, germinate. Okay, so what we're going to need to do for that is binomial distribution twice. So we're going to need to work out the probability that 15 or more seeds germinate, first of all. So then that gives us essentially the probability that a tray is successful. And then we're going to use that probability with a binomial distribution for the trays to work out the probability that 5 or more contain 15 or more germinated seeds. Good times. Alright. Okay, so let's let X be the number of seeds that germinate. And then I guess we should say in each tray. Then X as a binomial distribution. N is 24. And the probability is 0.55. Now we want at least 15 to germinate, so the probability X is greater than or equal to 15. Is 1 minus the probability X is less than or equal to 14. Okay, now we can use the calculators to work out the probability X is less than or equal to 14, and we will get 0.701. So this is 1 minus 0.701. Which gives us 0.299. So that's the probability that at least 15 seeds germinate in a tray. So now we're going to switch to the trays. So we're now going to let's use T for trays. So let T be the number of trays in which 15 or more seeds germinate. Then T has a binomial distribution. N is 10 and B is 0.299. Okay, now then, they said we want probability that at least half the trays do what we want them to do. So, probability that T is greater than or equal to 5 is 1 minus the probability T is less than or equal to 4. Again, we can use our calculators in to work out the probability that T is less than or equal to 4, and we get for that 0.851. So this is 1 minus 0.851, and that finally is 0.149. That was pretty. Okay, but C wants us to write down two conditions under which the normal distribution may be used as an approximation to the binomial distribution. Okay, so the two conditions are the probability needs to be very close to 0.5, so it can't just be any old value of P. And the other one is that N needs to be very, very large. And part D, we are told a random sample of 240 pea seeds was planted and 150 of these seeds germinated. Assuming that the company's claim is correct, use a normal approximation to find the probability that at least 150 pea seeds germinate. Okay, so to use a normal approximation, we need to find the mean and variance of the binomial distribution, which we can then use for the normal. So, we are given the mean and variance of the normal distribution. So, for us, mu is going to be n times p. So n is 240 here, and b is 0.55. That's why it was important to assume that claim is correct. So mu is 240 times 0.55. And that gives us 132. and then the variance is NP, so 132 times 1 minus P, so that's 0.45. And that gives us 59.4. So, X then is normally distributed with a mu of 132 and variance 59.4. So, we then want the probability that at least 150 seeds germinated. Now, because we are now using the normal distribution, we are thinking of the number of seeds as continuous. So, because of that, we need to think of the smallest number that would round up to 150, which is 149.5. So we want the probability that X is greater than 149.5. Again, we can do that on our calculators. So you want normal CD, lower bound is 149.5. Put in something massive for the upper, I'd put a million. Sigma is the square root of 59.4 and mu is 132. Work that in and you should get 0.0116. Okay, then the final part says, using your answer to part D, comment on whether or not the proportion of the company's species that germinate is different from the company's claim of 55%. So, what we have just shown in part D is that it's only 1.16% likely that out of those 240 species, 150 or more would germinate. So because that probability is very, very small, the company's claim is probably incorrect. For their claim to be correct, we would have wanted the percentage, the probability, to be a lot higher. So, from our answer, we would say it's very unlikely that the company's claim is correct. And that, my beauties, is the stats done. Thank God for that. On we go with the mechanics. And mechanics, what you got? So, at time t seconds, where t is greater than or equal to 0, a particle p moves so that its acceleration a meters per second squared is given by a equals 5ti minus 15t to the half j. When t is equal to 0, the velocity of p is 20i meters per second. We want to find the speed of p when t is 4. Okay, so speed is the size of the velocity vector. So it's the magnitude of v. not useful yet because we don't know what V is, but we do know that V is the integral of A with respect to t. Therefore, we can get then that V is equal to, now the integral of 5t is 5t squared over 2. Now we need to put a constant in there as well, so add c. So that's the I component, and then for j, we're going to have add, and then in the brackets, so t to the 1/2 integrates to t to the 3/2, we then divide by 3/2, so that's the same as multiplying by 2/3, 15 times 2/3 is 10, so we get minus 10 t to the 3/2, then we need a different constant, so let's call it d. So that's the j component. Okay, so we now need to find the constants. So we know that when t is 0, v is 20i. So t equals 0 then is going to give us ci add dj is equal to 20i. Therefore, c is equal to 20 and d is equal to 0. So, now we can say then that v is 5t squared over 2 add 20i and then minus 10t to the 3/2 j. Okay, now we want the speed when t is 4, so for that we need to find v when t is 4. So t equals 4 gives us that v is equal to, okay, so t to the power 2 is, sorry, 4 to the power 2 is 16, 5 times 16 is 80, divided by 2 is 40, so we get 60i and then we get minus, okay, so 4 to the power 3/2 is the square root of 64, which is 8. 10 times that is 80, so we get minus 80j. So, speed again is the magnitude of v, which is square root of 60 squared add 80 squared. Doesn't matter that it's minus 80 because we're squaring it. So 60 squared is 3,600, 80 squared is 6,400, so that gives us root 10,000, which is 100. And its speed, so it's meters per second. Boom. Okay, number 7. A rough plane is inclined to the horizontal at an angle alpha, where tan of alpha is 3/4. A particle of mass m is placed on the plane and then projected up a line of greatest slope off the plane. So that means, imagine in real life you come across a steep hill. The steepest way you can get up it is by going straight up. To go up it in a gentler way, you would walk up and across it. So the particle is being projected straight up the plane. We're told the coefficient of friction between the particle and the plane is mu. The projectile moves up the plane with a constant deceleration of 4/5 g. Part A, find the value of mu. Okay, so for this one, you are definitely going to want to draw a sketch. So there's our horizontal and the inclined plane. Let's put our particle there. Now, we know, first of all, it has a mass m, so the weight working down is mg. Now what we can also do is split that into its component forces like this. So that one is perpendicular to the plane and the other one is parallel to the plane. So the perpendicular one is working down and to the right, and the parallel one, well, it's the weight, so that's going to be trying to push the particle back down the slope. So that's working down and left. So we'll come back to those in a moment. We also know we're going to have the normal reaction to the plane. We also know there is overall the particle is moving up the slope, and we also know that working against us is gonna be friction. So what we know then is this angle here is also going to be alpha. Now we can use SOHCAHTOA to find these other two vectors. Now before we do that, I'm going to work out what sine of alpha and cos of alpha each are. So if tan of alpha is 3/4, that tells us that there is a right angled triangle with an angle of alpha, where the opposite is 3 and the adjacent is 4. Using Pythagoras, the hypotenuse is 5. So, sine of alpha is 3/5. Cos of alpha is 4/5. Okay, so using SOHCAHTOA, with regards to the angle alpha, the MG is the hypotenuse, the component working down and right is the adjacent, and the one working down and left is the opposite. So, by SOHCAHTOA, the adjacent is equal to the hypotenuse times cos of alpha, so that's 4/5 mg. Now we also know, because the particle is not moving up or down, then we know that the reaction force is the same but acting up. And then the other force is going to be the hypotenuse times sine of alpha, so 3/5 sine of alpha. Okay, so now that we know that, we can play with some equations of motion. So, we know that friction is mu times the reaction force. So we know the reaction force now is 4/5 mg, so that's mu times 4/5 mg Now we also know that the overall force working on the particle it has a constant deceleration of 4/5 g, so that's going to be minus 4/5 mg. Okay, so then if we sum all of the forces acting on the particle, if we take up the slope as being positive, then we have minus friction minus the parallel force, so minus 3/5 sine of alpha. We know that is equal to minus 4/5 mg. So we know minus friction minus 3/5 sine, minus 3/5 mg we know that is equal to minus 4/5 mg. Now we know that friction is mu times 4/5 mg, so minus mu times 4/5 mg minus 3/5 mg is equal to minus 4/5 mg. Okay, lots of common factors here, so everything is negative, so we can get rid of that. Everything is divided by 5, we can get rid of that. Everything as a factor of mg, we can get rid of that. So now we can say for mu add 3 is equal to 4. Therefore, mu is equal to 1/4. Okay, then we're told the particle comes to rest at point A on the plane. Part B, determine whether the particle will remain at A, carefully justifying your answer. Okay, so when it's at rest, so let's say it's at the point A now, so it's been projected up the slope, so what it's going to try and do is go back down the slope. So the only force acting down the slope is going to be the 3/5 mg. Now, fighting against that will be friction. So we know the friction now, because we know mu, the friction was mu times 4/5 mg. Now that we know mu, it's 1/4 of that, so that's 1/5 mg. So 3/5 mg is greater than 1/5 mg. So the particle will move back down the slope because it overcomes the friction. So it will not remain at rest at A. Okay, number 8. So in this question, I and J are horizontal unit vectors due east and due north respectively. So I is east, J is north. A radio-controlled model boat is placed on the surface of a large pond. The boat is modelled as a particle. Of course it is. At time t equals 0, the boat is at the fixed point O and is moving due north with a speed of 0.6 meters per second. Now what that means is if it's only moving north with a speed of 0.6 meters per second, that means its velocity is 0.6 j. We're told relative to O, the position vector of the boat at time t seconds is r meters. At time t equals 15, the velocity of the boat is 10.5 I minus 0.9 j meters per second. The acceleration of the boat is constant. Part A. Show that the acceleration of the boat is 0.7 I minus 0.1 j meters per second squared. Okay, so as I said then, we know so at t equals 0, now we're going to take this as our initial velocity in u. So that's 0.6 j. And then at t equals 15, our velocity, so we're now going to call that v, is uh, 10.5 I minus 0.9 j. So, we're going to need to that we know u, v, and t. So, we can use v is u add at. So, we know then that 10.5 I minus 0.9 j is equal to 0.6 j add 15a. Now if we subtract the 0.6 j, 10.5 I minus 1.5 j is equal to 15a. Therefore, divide by 15. A is 0.7 I minus 0.1 j. But B wants us to find R in terms of t. So, R essentially is displacement. So, if we look at that, we can use S is equal to ut add 1/2 at squared, except S is R. So, we know then that R is ut add 1/2 at squared so that's 0.6 jt add 1/2 of 0.7 I minus 0.1 j t squared. So it's not very neat, but that form would do it. Okay then, but C wants us to find the value of t when the boat is northeast of O. So northeast is exactly halfway between north and east. So that means the I and j components of R have to be equal. So we should probably start by saying that. So for northeast, of O, I, and J components of R must be equal. So that's going to give us that. So for I, we just have 0.7 t squared over 2. And for j, we have 0.6 t minus 0.1 t squared over 2. Okay, so we want to solve that for t. Now we can see that t equals 0 would be a solution, but that makes no sense because at t equals 0, the boat is at O. So we ignore that. So if we multiply through by 2, we will get 0.7 t squared is equal to 1.2 t minus 0.1 t squared. Multiply through by 10, 7t squared is equal to 12t minus t squared. And we know that t equals 0 can't be a solution, so we can divide through by t. So 7t is equal to 12 minus t. So 8t is equal to 12. So t is 3/2 or 1.5 seconds. And but t wants us to find the value of t when the boat is moving in the northeast direction. So when the velocity is northeast. So we're going to need to find the velocity vector, which is the derivative of r, and again set the component coefficients equal to each other and solve for t. So if r is this guy down here, then velocity is going to be the derivative with respect to t. So we're going to get it there. We are going to get 0.6 j Now, all that we need to differentiate here is the t squared. So we will get 2t, which cancels nicely with the half. So we're going to get add 0.7 ti minus 0.1 tj. Okay, so we have 0.7 Ti. And then we have add 0.6 minus 0.1 Tj. So this means then that 0.7 T must be equal to 0.6 minus 0.1 T. Okay, so if we add 0.1 T, let's also multiply 3 by 10, and we're going to get 8 T is equal to 6. So T is equal to 3/4. Okay, number 9. A uniform ladder AB of length 2A and width W has its end on rough horizontal ground. The coefficient of friction between the ladder and the ground is 1/4. The end B of the ladder is resting against a smooth vertical wall as shown. A builder of weight 7W stands at the top of the ladder. To stop the ladder from slipping, the builder's assistant applies a horizontal force of magnitude P to the ladder at A towards the wall. The force acts in a direction which is perpendicular to the wall. The ladder rests in equilibrium in a vertical plane perpendicular to the wall and makes an angle alpha with the horizontal ground where tan of alpha is 5/2. The builder is modelled as a particle and the ladder is modelled as a uniform rod. Part A answers show that the reaction of the wall on the ladder at B has magnitude 3W. Okay then, so let's put what we know on the diagram. So we know at A, the assistant applies a force P and that acts to the right. We also know down here there is going to be friction. We don't at the moment though know which way friction is acting. Is it working with P or against P? For part A we don't need friction, so I'm not going to put it on. Now we also know that there is going to be a reaction between the floor and the ladder. So that's going to be working straight up and we'll call that R. Now, we need to be very careful as well because we were given the weight of the ladder, not the mass. So there's no G involved here because the weight is W. Now the weight of an object works down through its centre, so the weight of the ladder is going to be working down A along the ladder. We know the weight again of the builder who is standing here we know his weight is 7W. Now we also know there is a reaction with the wall, so that acts perpendicular to the wall, and we're going to call that S. Now, what can we do with everything we know? Well, we can work out some moments. We know the ladder is in equilibrium, so the moments are in equilibrium. So, if we work out some perpendicular forces, we know at the middle of the ladder that angle is alpha, and then just as we've done in a previous question, the perpendicular force is W cos alpha. Up here, this one is going to be 7W cos alpha. And that's working down into the right. So, if we think about those moments, first of all, they are both going to be working clockwise, so technically they are negative. So the moment at the centre of the rod is A away from the point on the ground. Let's just do it here. So we can say then that minus AW cos alpha and then the moment at B is going to be minus 2A times 7W cos alpha, so that's minus 14 AW cos alpha. Okay, so now we need to find the moment being applied by the wall. So we know by alternate angles that this chap here is also alpha. Now we can make a triangle with the ladder. So what we want is this perpendicular force that is opposite to the angle. So sine of alpha is that length over S, so that length is S sine alpha. So that's the perpendicular force acting on the ladder from the wall. So the moment from that is acting anti-clockwise, so it's positive, and it's 2A away from the point on the ground. So now we're going to add a s sine alpha. Now because we know this is all in equilibrium, this is equal to 0. So, we have then minus AW cos alpha minus 14AW cos alpha, so that's minus 15AW cos alpha add to a sine of alpha to a s sine of alpha is equal to 0. Now everything has a factor of a, so I'm going to get rid of that and add the cos term to the right. So we're going to get 2as sine of alpha. No, we're not, because the a is gone. We're going to get 2s sine of alpha is equal to 15w cos alpha now, because we know alpha is not equal to 90, we can divide through by cos alpha. So we get 2s tan alpha is equal to 15w Now we know that tan alpha is 5/2, so we now know then that 2s times 5/2, so that's 5s is equal to 15w. Therefore, S is indeed 3w. Okay, then part B, we want to find in terms of W the range of possible values of P for which the ladder remains in equilibrium. Okay, so now that we're thinking about P, we need for the horizontal forces to be in equilibrium. Now, as I said before, we don't know which way friction is working. It might be working against the force that the assistant applies, or it might be working with that force and working against the ladder slipping. So, what we do need to do first of all is find friction. So, what we know then, we know friction is mu times R. So, we know that mu is a quarter. We don't know R. So, what we do know is the vertical forces are in equilibrium. So, that means then that R minus W minus 7W is equal to 0. So R is 8W. Now that then means that friction is 2W. Okay. Then we should probably mention that the horizontal forces are in equilibrium. Okay, so there are two cases. Now, either friction is working to the right as well, so that would mean that P add friction minus 3W, which I forgot to put on, so case 1, P add friction minus 3W is equal to 0. So P add 2W minus 3W is equal to 0, therefore P is equal to 1W, or if friction works against P, then P minus friction minus 3W is equal to 0. So P would equal 5W. So what we have found is a minimum and a maximum value for P. So the range is that P is greater than or equal to W, less than or equal to 5W. Okay, then for part C, often in practice, the builder's assistant will simply stand on the bottom of the ladder. Explain briefly how this helps to stop the ladder from slipping. Okay, so the builder's assistant then is going to be stood on the ladder at A. So, now instead of his force being acting to the right, his force is now going to act directly down. Now, the first thing we should mention is that because his weight is going to be acting down through point A. The moments about A are going to be unchanged. So none of the forces up the ladder are going to be changed. So that's not going to affect the reaction force on the wall. Now, because he is applying a force directly downwards, then the normal reaction of the ground on the ladder is going to increase. If the reaction force increases, so too does friction. So by increasing friction, he is helped to stop the ladder from slipping. Number 10, the final question of this ordeal. So we have projectile motion. So a boy throws a stone with a speed u meters per second from a point O at the top of a vertical cliff. The point O is 18 meters above sea level. The stone is thrown at an angle alpha above the horizontal, where tan of alpha again is 3/4. The stone hits the sea at the point S, which is at a horizontal distance of 36 meters from the foot of the cliff, as shown in figure 2. The stone is modelled as a particle moving freely under gravity with g equals 10 meters per second squared. So that means no resistant forces horizontally. Find part A, the value of u. 6 marks. Right. Okay. So, what we're going to do is solve that for the x and y components of this force u. So, first thing we're going to do is split it into its components. So, this guy here then is alpha. So, we've done this in a fair few questions already. The horizontal is u cos alpha, and the vertical is u sin alpha. Now we can find numerical values for those. The sines and coses anyway. So because we know tan alpha is 3/4, we're in the old 3, 4, 5 triangle. So sine alpha is 3/5. Cos alpha is 4/5. So, if we now do that for x and the horizontal and vertical motions, then we know that the displacement for x is 36. The initial velocity in x is u cos alpha, so 4/5 u. We don't know v. We know that a is 0. and we don't know time. Now, for the vertical, we know vertical displacement is going to be 18 meters below where it started, so minus 18. The initial velocity vertically is u sine alpha, so 3/5 u. Again, we don't know v. We know that our acceleration is minus 10. And again, we don't know time. Okay, so what can we do with Suvat then? So, looking at the horizontal, we have S, U, and A. So, if we use S is ut add 1/2 at squared, 1/2 at squared is 0, so we can get that S is ut. So from the horizontal motion, S is equal to ut. So 36 is equal to 4/5 t. Sorry, 4/5 ut. Now, all that's going to allow us to do is get an expression for t in terms of u. So, if we divide by 4, we get 9, times by 5, we get 45. So, t is 45 over u. Okay, so what we're going to do now is use vertical motion to get another equation that's going to involve t. We can now eliminate t in terms and substitute this expression in u. So, from the vertical, now we can actually use the same equation. So again, we can use S is ut add 1/2 at squared. So this is going to give us minus 18 is equal to, so u here is 3/5 big U. Now, times t, and t is 45 over u. And then we're going to get So it's plus 1/2 at squared, so that's minus 5 times t squared, so 45 squared over u. Squared. Okay, so so we have minus 18. Now, in this first term on the right, the u's cancel. 3/5 of 45 is 27. So we have minus 18 is equal to 27 minus. Now something nice is going to happen here with the 45s, so I'm going to leave this as 5 lots of 45 squared over u squared because if we subtract 27 we can get minus 45 is equal to minus 5 times 45 squared over u squared Now if we divide both sides by minus 45, everything becomes positive. So we get 1 is equal to 5 times 45 over u squared. Multiply through by u squared. So u squared is 5 times 45, which is 225. So we actually get a nice answer. U is 15 meters per second. Okay then, part B wants us to find the speed of the stone when it is 10.8 meters above sea level. Giving your answer to 2 sig figs. Okay, so again, this speed is going to have a horizontal component and a vertical component. We can find the horizontal component straight away. We now know the value of u, and there were no resistant forces horizontally, so it's going to stay the same. So we know the horizontal motion well it was 4/5 of u. U is 15, so it's 4/5 of 15, which is 12 meters per second. Okay. Now, we need to do something clever for y. So, let's think about this now then. So, we want the stone to be 10.8 meters above sea level, so its displacement is minus 7.2. Now again we can work out its initial vertical speed. It was 3/5 u, so that's 3/5 of 15, which is 9. Now v is what we need to find. A, again, is minus 10. And we don't know time. So, what can we use for that then? So, v squared is u squared add to a. This looks very nice. So, that means then that v squared is 9 squared 81 add 2 times minus 10 times minus 7.2. So that's going to be positive 144. So v squared is 225. Therefore, v is 15. Okay, so we know at this point the motion is going to be down and to the right. So let's call this any old thing. Let's call it x. X is cool. So we now know the downward component has a magnitude of 15. Horizontal has a magnitude of 12. So x squared is the square root of 12 squared and 15 squared, which is 369. Now if we square root that to two significant figures, we get 19 meters per second. Okay, then the final part wants us to suggest two improvements that could be used to improve the model. So, let's think about what we've done. We've modelled the stone as a particle. It's going to have dimensions, so take those into account. We've assumed no horizontal resistant forces. Air resistance is a thing. The stone is going to be spinning, so that's going to affect things. Anything like that, and we are groovy. And on that, the paper is done. Hope you found it useful. Pretty tricky stuff. Don't forget the links to all of my existing past paper walkthroughs are down below, as well as all my other content. Give us a thumbs up, get subscribed, drop us a comment with any requests. Take it easy, take care.